is Søren Engelsen, another chance participant. The title of his speech is Evaluating the Metabolic Profiles of People at Risk of Poverty in Comparison to Those from Affluent Groups. And it was one of the tricky questions in the chance project to find a biomarker, or more than one biomarker, to distinguish ROP and affluent people.
Thank you, Alexandra, and thank you to the coordinators for including a small country up in the north, Denmark, to this interesting project. I am going to say a little bit of what we have achieved in the so-called Work Package 3 concerning metabolomics in the CHANCE project. And a little bit of background. Oops. Just trying to see if this works. Yes, a little bit of background. Metabolomics is not a very old technique. It was introduced by Engelsen at Imperial College as metabonomics, understanding the metabolic responses of living system to pathophysiological stimuli via multivariate statistical analysis of biological NMR spectroscopic data. And also in the plant metabolomics area, Oliver Fien defined metabolomics as the link between genotypes and phenotypes. But what is interesting in nutrigenomics is that we can actually establish a link between the genome and quality and health and consumer interest by metabolomics. And of course we can measure the metabolome many different ways, and the next slide is sort of a comic strip showing the technology chain in how metabolomics works. So first you have to have a hypothesis, and in our case it was the risk of poverty versus affluent diets, not the Mediterranean versus the Nordic diet. And we also decided for collecting only urine from the human metabolome. We decided only to use NMR spectroscopy, not other possible metabolomic platforms like DCMS, LCMS. And then of course you obtain a huge amount of spectra, and you want to do multivariate data analysis. And if you have in luck, you will also find differences which are systematic according to your experimental design. So we think that metabolomics has a lot of potential. It can assess the metabolic consequences of critical diets for individuals at risk of poverty, and it can help to establish biomarkers for healthy and deleterious foods. It has potential to evaluate and develop stratified nutrition to different population groups. So that was sort of the onset of our project. So we decided to use this. Maria has told you a little bit about the experimental design, but we had 5 collection centers, and Finland, Lithuania, Serbia, Italy, and England. And then we decided to have 2 measurement sites. One in Italy and one in Denmark. So we were transporting the urine samples collected at the recruitment sites to 2 measurement centers, one in Florence and one in Copenhagen. So a major task of our metabolomics work package was actually to standardize, to make sure that the NMR equipment and the urine collection and everything was exactly the same, so the results that we obtained in Florence and in Copenhagen were comparable. So there was a lot of standardization concerning the urine collection and urine collection, storage and transportation, and a similar amount of different parameters for acquiring NMR spectrum. Sample handling, preparation of solvents, automation setup, acquisition, processing, and everything. So this was not trivial at that time to have 2 NMR spectrometers providing the same data when measuring the same samples. So we were setting up a ring test, and we were considering different things that we want to establish acceptance criteria. eliminate unwanted sources of variance, and we wanted to establish pre-processing so that we could match the data coming from Florence and Copenhagen. So we set up a number of acceptance criteria. We investigated the water suppression method used at both sites. We investigated normalization. Urine is not an easy measurement object because you will have different dry matter, so you will have very different urine spectra even from the same person at different times of the day. So we had to also investigate normalization, and finally also we had to implement new alignment techniques. But we ended up making an efficient protocol so we could quantitatively compare similar samples at Florence and Copenhagen sites. So we really got very low in the variance between the sites, and we also had to develop an alignment protocol or algorithm actually, which is now more or less globally adapted to NMR spectra and even to chromatographic data.
You analyzed the urine, isn't it?
Yes. Did I say something else?
No. Urine.
Yeah, urine, yes. Okay, so this is the data collection that we ended up having at last. So approximately 500 samples from each recruitment site, and ending up with 2,732 samples. So we had a huge data collection site here, and now it's these samples that we wanted to process. So in our raw data matrix, we had these 2,732. We needed to do some data cleaning, organization, sorting, so we could identify the different samples, pre-processing, because of course the samples were randomized when we measured, pre-processing, averaging, because we had 2 time points, so we decided in many of our comparisons to superimpose the 2 or to average the 2 time points, and we also had to do scaling. And all this ended up in the CHANCE database. The CHANCE database, I will not say too much detail, but it was decided that we would actually bin the data a bit in order to compress the data. It turned out not to be an important issue, so we went down from the 58,000 variables to a much lower number. This is now implemented in a spreadsheet, and where we can identify volunteers, spectrum number, bin values, and token code, so we can identify these objects in the database. Then the database, NMR database, was also aligned with biometric database and the nutrient databases. And of course, what we wanted to do in CHANCE project was to see if we could get any information out of the metabolomics which can be related to the status of the subjects as being ROP or affluent. And the primary tool that we have for this is multivariate data analysis or pattern recognition. So we want fingerprinting of populations with different economic income and different diets. We were at scratch, aware that this was a serious challenge to scrutinize and unravel tiny changes in the metabolic profiles, also because the ROP affluent status is not a very firmly established thing. So we wanted to use untargeted analysis and also to do a targeted analysis. I'm just showing here some of the simpler methods, but we also used advanced method. So this is how our complete data set look like if we use a simple principal component analysis of the 2,700 and something spectra. Each point in this score plot are representing a complete NMR spectrum. And here we have some sort of a consensus group. So we have these 2,700, and it turned out that these ones out were what we call outliers, and they are defining people with trace amounts or larger amounts of glucose in the urines, but since diabetic was an exclusion criteria, these has to be pre-diabetic subjects from our investigation.
The subject didn't know that they were diabetic.
Yes, exactly. Yes. So pre-diabetic or unaware. We also looked if there was any influence of the recruitment centers, and this is the global model, which is colored according to the different recruitment centers, and it's pretty randomized in the global model. But if we look more detailed, like Finland versus UK, we could actually see a clear separation between these two, also both in the global model and in the focused model. This is primarily due to different ethnicities. In Finland, it's Finnish people, and in UK, it's actually Pakistani ethnicity. And they differ in their diet, and we think that it's normal that they are actually separated in this score plot. We were also looking at gender difference, what is the influence of gender, and it was not completely clear from the global model, but if you look into more detailed models from the recruitment side, you can actually see there's a pretty clear differentiation between genders in the metabolomic profiles. But of course, what we wanted to do was to distinguish between the ROP subjects and the affluent subjects. And this is not really easy to see, but there's not really a separation between the two classes. So then we wanted to investigate all the different recruitment sites, and quite disappointingly, it was not really possible to find clear trends in any of the different recruitment sites, Finland female, Finland male. Even if we divide it up into gender, it was not possible for us to find a clear separation between ROP and affluent people. We also tried to do more targeted analysis. This is ECVA, Extended Canonical Variate Analysis. And by this kind of method, it's actually possible to pretty clearly see the different recruitment sites. But you also have to be aware that even though we can actually classify and there is a shift between the different recruitment sites, we still have a large number of misclassification. It's in the order of 400 out of the 2,700 subjects or samples. We also tried to do PLSDA because we wanted to try to overfit the data, but fortunately we have 2,700 spectra, so it's not really possible to overfit it. And this is how PLSDA models look for affluent and ROP. And this is the predicted versus measured, so there should be a separation on this axis between the two classes, and there's a huge overlap. And here we did the same exercise just for the Italian population, and even for this population, which is homogeneous in terms of gender, it's only females in Italy. It's not possible to do a good separation. Recently, we have also tried to apply some new methods which were not around when we originally thought out or when we designed the project. There's something called ANOVA, Simultaneous Component Analysis, ASCA, which is a very efficient tool for balanced data set. Unfortunately, our data set is not balanced at all. We have one recruitment site which was only female. We have other recruitment sites which has more ROP and affluence and so forth. But of course, we can take out a subset of our change data set and make it balanced. If we do so, we end up having 594 samples, which is actually, and then we can apply this ASCA model, which is able to partition the variance of our NMR spectra into a gender-specific data set, a country-specific data, an ROP-specific data set, and also between different interactions between the model. And unfortunately, we have not been able, it doesn't seem like it's significant, but nevertheless, I would show you it's just below significant. But this is how the ASCA scores looked for the ROP affluent, and there's clear indication. The shift between the two is marked by the big dots here. Is not really significant. We are still working on it, but we don't think we will end up there. But we see a much larger spread in the ROP than we have in the affluent. So we are now turning towards new data technology where we are trying to describe this larger spread apparently in the ROP people. So the conclusions so far of our metabolomics investigation is that the urine metabolome is strongly related to country and ethnicity. Cultural dependent dietary habits are clear sources of variance. We also see that there's a correlation. So far we have not been able to reveal a correlation between the human metabolome and the economic status. If it is present, it is well hidden, but we have not entirely given up. But we think that what is more interesting is that there seems to be a larger spread in the ROP subject or the ROP population, and we think of this as ROP. The larger spread could be that unhealthy dietary habits can be more diverse than the more sort of healthy center status. But we also see from the point of view of urine metabolism that the human organism is an excellent leveler, averaging out even quite different dietary habits. So if we take the outlook of our metabolomics work package, we have successfully established a standard operating procedure for urine collection and measurement, different measurement sites and collection sites. We have created a biobank of approximately 2,700 urine samples of European citizens, which can be further investigated with more sensitive platforms, omics platforms. Currently, we do not know if we have to destroy this biobank, but so far it exists. We have also created a database of 2,700 urine high-resolution NMR data, which has been aligned with nutritional, socioeconomic, and anthropometric metadata for data mining studies. And also, I think it's a conclusion that data fusion and correlation analysis between the spectral data and nutritional data has proved to be even more challenging than originally expected. So the urine sample and data collection made by the TREND consortium, I think, deserves to be further exploited in the future. And I think that's it for me. Yeah.